I thought this week about geodesics because next week we start thinking about geodesics in differential geometry, and also there was a talk last week about the mass gap problem, one of the millennium problems, and it's kind of an interesting quest for a mathematician to look for toy models which are simple and can be used for experiments. And this week I was working again on this discrete geodesics, right? We have talked about this quite a bit already. It works in any simplicial complex, any dimension. You just take a simplex, and what you can do is you can, if you have a manifold structure, for example, you can every wall, every q-1 dimensional simplex has exactly two simplices attached, like here, right? Every wall, every two-dimensional wall has two simplices. So you can go from one to the other, and you can design a dynamical system. So one of the things I really want is determinism. I also want reversibility, that happens here. I want locality, that the particles only interact locally. I want causality, that its speed is a speed of light limit. And I don't want free parameters. I'm getting allergic for all this AI stuff where you have billions and billions and billions of parameters, and it's just a glorified data fitting scheme. And 1 over infinity, if you have infinitely many parameters, 1 over infinity is 0. We don't want any parameter. 0 parameter, there should be no choice. And there is still choice for the interaction. Here I have just implemented things now on a cellular automata level. You know, there are different ways how you can talk about particles. You can just make a list of the particles and say where they are in space, or that's simpler, you just say how many particles of each type, if you have finitely many types of particles, are there at each point. If you have just one type of particle, then you have just a z, integer valued map, which is also called a divisor. Later, maybe next week, I will talk about the case of when you have a Gaussian integer or quaternion valued divisors, because there are some particle structures there which you know, look like the standard model. You know, the standard model has really this division algebra structure, and there are only finitely many division algebra, there are only finitely many forces, so types of forces, so it's very natural to make this thing. All these theories, general relativity, quantum mechanics, and the standard model are somehow, you know, very simple pillars in, you know, for a mathematician. If general relativity is just about geodesics and about the, you know, variational problems like the Hilbert action, quantum mechanics is just exponential map in a Hilbert space. And just from an operator gives you a dynamics, and the standard model somehow is related to this division algebra. So we would like then to go with the division algebras, and I will talk about this maybe next time. So for now I was just actually kind of worrying about how to implement this in such a way that we don't have the limitation to work with, you know, a few hundred or thousands of simplices, but in order to talk about millions and millions of particles on millions of simplices. And the simple thing, I'm very fond of cellular automata. All this model which I kind of looked at the beginning of this year is of course a cellular automaton. It just the particles are moving just to the next stage, and you can you know, write this as a cellular automaton. And I've done that now, just implemented. Again, these are all the lines which you have. Before that I had about 12 lines for a general simplicial complex. Now this is just the lines which I need for describing it on a flat lattice. Flat lattice is the Clifford lattice, and it's also kind of the Clifford torus if you identify left, right, top, bottom. And what you can do is now, just for every orientation of the simplex, we can just design a matrix. So because here we have two lattice points for each square, like here, this is a nice triangulation of the two-dimensional sphere, and in this case there are just 4 vertices with curvature 1/3, and we have talked about this, and 4 with curvature 1/6. 4, 6 plus 4 times 1/3 is 2. So the total curvature is equal to 2, like it should be for any two-dimensional sphere. In this case, what is nice about this geodesics, and I talked about this, every node, if you realize them in space, arbitrary dimensions, this is always flat. So that's what you also want to have in the continuum. If you draw a geodesic and a tube around it, then this is flat. Flatness, that's really kind of like the geodesic curvature is 0. And we talk about this in differential geometry also. So it's a very natural evolution because the tubes you get have 0 curvature. And that's not only in the flat case, that's in any simplicial complex, which is has a manifold structure. So here, this is kind of just a little engineering task. I spent a couple of hours programming that, especially Friday, last Friday, yesterday, and I spent a couple of hours just focusing on that without doing, and that's what I wrote down in one coffee shop, is just to find the rules, right? You want to find, if this particle moves here, we want to kind of find the rules, and then implement it in Mathematica. That's here, that was another coffee shop. So you have about 4 hours, 2 hours here, 2 hours here, and that's the implementation of that whole game. So we have matrices here, matrices which tell, for example, what happens at every node of this type of plackets, of this type of simplices, right? So that's 1, 2, 3, that's the orientation 1, 2, 3. So there are 6 possible orientations, and so the particles can move in 6 possible directions here. But it looks pretty nice if you look at it, and I already started also to look at the case of interactive particles, and it's not more complicated, a little bit more complicated, because you have to say in this case you do that, in this case you do that, but the complexity is not much bigger, and it doesn't matter how many particles you have, the interaction really works as fast as here. And so you can make experiments, you can have particle cloud here, particle cloud here, you put them together and then let them interact, and then study different interaction rules. And again, here we don't want any choice for an interaction rule. So what I did in the case before, I just said we have positive particles and negative particles, and then we count the number of particles which are at the specific simplex, and this decides how we move. And it has to be commutative, right? If you have 10 particles coming at the same point, this should be a deterministic version. It should not matter which particle is first. So it should be a commutative law to have a deterministic finite thing. And especially then in the number theoretical case, it should also go over to the division algebras. It should go over to the complex, and should go over to the Hurwitz primes here. Here we have lepton structures, here we have hadron structures, we have we see something like electrons and neutrini, and here we see some things like mesons and baryons. So this is a place where we can play with a toy model. That's it for today.
you.